Right now, diamonds are literally raining down through the atmospheres of planets in our solar system. Scientists believe diamond rain is occurring on Neptune and Uranus, where methane gets crushed by immense pressures deep in the atmosphere, forming diamonds that become heavy enough to fall like rain. What sounds like pure science fiction is actually backed by strong laboratory evidence and detailed modeling, and the scale of this cosmic phenomenon will blow your mind. These diamonds form at pressures of 10 to 80 gigapascals and temperatures above 2000 Kelvin, with the innermost regions reaching 7000 Kelvin and pressures 6 million times Earth's atmosphere. At such extremes, a single cubic inch of atmosphere weighs as much as a car, while temperatures soar beyond 12,000 degrees Fahrenheit. Uranus and Neptune are primarily composed of hot, dense clouds of water, ammonia, and methane. Their outermost layers sit around 3,000 degrees Fahrenheit, with atmospheric pressure around 200,000 times that of Earth. But as you descend deeper into these worlds, something extraordinary happens to the methane molecules. Methane's chemical formula is CH4, one carbon atom bonded to 4 hydrogen atoms. Under the crushing weight of these planetary interiors, those bonds don't just stretch or bend, they completely shatter. Under such heat and pressures, ammonia and methane become chemically reactive. The carbon atoms, freed from their hydrogen partners, get squeezed together with such incredible force that they lock into diamond's crystalline structure. Meanwhile, the hydrogen gets compressed into metallic hydrogen, a substance so exotic it barely exists on Earth. Recent experiments at the European X-ray free electron laser facility have shown that diamond formation from carbon compounds starts at lower pressures and temperatures than previously assumed, meaning diamond rain forms at shallower depths than scientists first thought. Researchers generated pressures and temperatures of more than 2,200 degrees Celsius using diamond stamp cells and lasers, with the stamp cells functioning like a mini vice, squeezing samples between 2 diamonds. The sheer scale of the transformation is what makes this process so counterintuitive. Current estimates indicate that diamonds may grow over millions of years on Uranus and Neptune, potentially creating meter-sized gems. Diamonds the size of boulders form not in Earth's crust over geological time, but fall like hail through alien skies. The diamond rain probably influences the formation of the complex magnetic fields on these worlds, creating a feedback loop between atmospheric chemistry and planetary magnetism. Scientists predict these diamonds could weigh millions of carats each, transforming over thousands of years as they slowly descend through the dense atmospheres. A high-quality, 1-carat natural diamond costs between $4,000 and $6,000 on Earth's market. A single million-carat diamond from Neptune's storms would theoretically be worth between $4 billion and $6 billion using Earth diamond prices. That's more than the GDP of many nations, falling as precipitation. The sheer volume of this phenomenon makes Earth's most spectacular weather systems look trivial by comparison. Deep within these distant ice giants, crushing pressure and extreme heat forge a glittering storm, causing trillions of carats of solid diamond to rain down through their atmospheres. While a major thunderstorm on Earth might produce millions of raindrops, Neptune and Uranus are generating what amounts to a constant downpour of precious gems, each storm system potentially containing more wealth than entire continents on our planet. The process operates on geological timescales that dwarf human experience. The diamonds may spend thousands of years growing to weigh millions of carats, slowly sinking toward the core through the atmosphere and mantle as heavy rain that puts our own downpours to shame. Laboratory experiments suggest that within Uranus and Neptune, where there have been many millions of years to grow diamonds, meter-sized carbon crystals can form. Diamonds the size of boulders, each worth more than the entire global diamond market, drift downward through alien skies for millennia. Over thousands of years, the diamonds slowly sink through the planet's ice layers and assemble into a thick layer around the solid planetary core. This creates a scenario where the cores of these planets could be surrounded by diamond shells worth more than the combined wealth of human civilization. Layers of crystallized carbon that have been accumulating for millions of years. The economic implications stretch beyond mere numbers. If we could somehow harvest just a fraction of 1% of Neptune's diamond rain, it would crash Earth's diamond market overnight, making these precious stones as common as pebbles. The very concept forces us to reconsider what we consider valuable when the universe operates diamond factories on a planetary scale, running continuously for millions of years. Given that Neptune and Uranus could have diamond shells worth more than all human wealth combined, would you rather explore one of these diamond rain planets or mine asteroids for precious metals? Comment your answer below. But here's what makes this cosmic treasure hunt even more mind-bending. Saturn and Jupiter create diamond rain through a completely different mechanism that begins with giant lightning storms spotted by spacecraft in the upper clouds. These celestial behemoths are known for their spectacular and powerful electrical discharges, far surpassing anything seen on Earth, with a single lightning strike delivering immense energy that effectively shatters the robust molecular structure of methane. Dark, stormy regions seen on infrared images correspond to the breakup of methane molecules into carbon, most probably soot particles. Around 0.3% of Saturn's atmosphere is carbon, mostly in the form of hydrocarbons such as methane gas, and lightning storms high up in its thunderstorm alley can turn this methane to soot. The transformation process follows a precise sequence as the carbon particles descend. Once formed, non-crystalline carbon sinks down through the atmosphere until it reaches an altitude where increasing pressure converts it to graphite, similar to the lead in a pencil. By 1,500 kilometers down, the graphite has begun its transition, and by 6,000 kilometers, that graphite has hardened further into solid diamond. These diamond chunks could reach sizes of about a centimeter in diameter before continuing their descent into the scorching depths. As these glittering diamond hailstones plunge deeper into Saturn's interior, nearly 30,000 kilometers down, the immense heat and pressure cause them to melt into a liquid state. Scientists estimate that roughly 1,000 tons of diamonds fall each year on Saturn, with about 10 million tons of diamonds stored in the gas giant at any given time. What makes Jupiter and Saturn's diamond rain particularly fascinating is the sheer atmospheric violence that triggers it. The energetic lightning storms in Saturn's atmosphere dissociate molecules into atoms, ions, and plasma, creating a feedback loop between electrical activity and diamond formation that operates on scales utterly foreign to Earth's weather systems. As diamond particles form, they drag gas and ice with them as they descend from the outer to inner layers of the planet, slowly sinking deeper into the planetary interior in response to gravitational forces. Over thousands of years, a single diamond grows to the size of a marble, pulling surrounding material along in its wake, and creating currents of conductive ice that flow like slow-motion rivers through the planet's interior. The diamonds stir the ice as they fall, forming above a layer of conductive ice. This creates something unprecedented in our solar system, planetary-scale mixing driven by falling gems. Each diamond acts like a cosmic stirring rod, churning the planet's interior as it sinks toward the core. The process operates continuously across millions of years, with countless diamonds creating a complex circulation system that fundamentally shapes these worlds from the inside out. This diamond rain has a stronger influence on the formation of their unusual magnetic fields, which aren't generated in the planetary core but in a thin layer of conducting material. The falling diamonds don't just disappear into the depths, they actively sculpt the magnetic environment of entire worlds. Unlike Earth's magnetic field, the fields around these icy planets are not symmetrical and don't extend from each pole, creating magnetic signatures unlike anything else in our solar system. The timeline of this process stretches across millions of years. A diamond that forms in Neptune's upper atmosphere won't reach the planet's core for eons. Along its journey, it will encounter increasing pressure and temperature, potentially growing larger as it absorbs carbon from the surrounding environment. Pressure and temperature continuously increase deeper inside the planet. And even in extremely hot regions, the ice remains solid due to crushing pressure. This means diamonds falling through Neptune experience conditions that would vaporize any Earth material, yet the ice around them stays solid, a state of matter that exists nowhere else in our solar system. The cumulative effect creates planetary interiors unlike anything we've ever observed. Layer upon layer of diamond-stirred ice, magnetic fields, shaped by falling gems and circulation patterns driven by the gravitational pull of crystallized carbon. These worlds aren't just planets, they're dynamic systems where the formation and descent of diamonds fundamentally reshapes their internal structure across geological timescales. Diamond rain on Neptune and Uranus reveals something far more profound than two isolated oddities in our solar system. Recent research suggests that diamond rain would also be possible on gas planets smaller than Neptune and Uranus, so-called mini-Neptunes. one of the most common types of exoplanets found outside our solar system. These worlds don't exist in our solar system, but they populate the galaxy by the thousands, creating a universe where diamond rain could be falling on countless worlds across the Milky Way. The scale of this phenomenon becomes staggering when we account for exoplanet populations. Mini-Neptunes are roughly 9 times more common than Jupiter-sized planets in the galaxy. This means diamond rain isn't just happening on 2 distant worlds in our outer solar system. It's likely occurring throughout the galaxy on a scale that dwarfs our imagination. Every time astronomers discover another mini-Neptune orbiting a distant star, they're potentially finding another world where diamonds cascade through alien atmospheres. Some of the most exotic examples push diamond formation into entirely new realms. Exoplanets orbiting pulsars with helium and carbon-dominated atmospheres form diamond clouds under conditions that would be impossible on Earth. One such world, located 2,000 light-years away, orbits a collapsed star with such intense radiation that carbon transforms under pressures and temperatures that create atmospheric conditions where diamonds form in ways we're still learning to model. The implications stretch far beyond planetary science. Understanding how materials behave under extreme pressure informs not only planetary science, but also materials physics, energy research, and nuclear fusion. The same principles that turn carbon into diamonds in Neptune's mantle govern the behavior of matter inside stars and the cores of giant exoplanets. What started as a hypothesis about 2 distant worlds has revealed a fundamental process of planetary evolution that operates throughout the cosmos. Diamond rain might not be a rare oddity confined to Neptune, but a widespread feature of certain planetary types across the galaxy. The universe operates diamond factories on scales we're only beginning to comprehend, not just on Neptune and Uranus, but on thousands of worlds orbiting distant stars, each one transforming carbon into crystalline perfection under conditions that reshape our understanding of what's possible in the cosmos. Subscribe for more impossible space facts that are actually real. Stay searching.